Welcome and hello to the first official lecture in our deep learning course. These lectures will be focusing first on the rapidly evolving field, the natural language processing. As you might have heard of this GPT-4 and ChatGPT, which are making a very popular, famous thoughts about how these neural networks are modeling text data in a very efficient way and producing humanly results. So these couple of lectures will be a little bit theoretical as we are going to dive through the nitty-gritty parts of how these architectures of the classic part till the transformer are being structured together. It could also be a good inspiration for the NLP researchers that are thinking about developing more in this field. Uh, these also lectures are assuming that you have a prior knowledge of the fully connected neural network and how it is being structured and work, not very deep knowledge of it. Okay, so let's dive in. We will be discussing here some of the top famous applications that have been used recently during this field. For example, the speech recognition, converting the audio to text translation, which Google behind the scenes is using a deep learning model to model these text data and translating it into different language. Chatbot, as you have heard also of this ChatGPT, text summarization, like converting a bunch of documents into a single structured document, which is very efficient for news summarization, etc. These are not the only, but some of the most popular. There exist tons of other applications you can see in the natural language processing field, as it's a very expanding field. So let's get started with think about how we can model this type of data in our neural network. So thinking about the ideal properties or the ideal architecture of the neural network, we should think about 5 main properties in our mind. First thing is that it should has a memory. Like each sentence I'm saying now in your brain is being correlated with the previous sentences that I was saying in the first part of the video. Okay, so you should be aware of the context of this video, and in that case you should be using the memory in order to correlate the dependency across the inputs that I'm saying. So the neural network is the same way, should be modeling this dependency across the inputs. Another thing, it should be applicable for variable lenses. So it is not like the convolutional, or it is not like the images, which should be having just a fixed lens, a fixed sized image. No, the text data is pretty much variable length. So I can say different sentences with pretty much different lenses. So in that case, I should have a same function to be executed each time step without changing its parameters. So I need to have an architecture with a function that is flexible enough to pass through it a different variable sizes of length. And it should also produce the same dimension of output. The third important part is that the neural network should maintain the order of the sequence. Like if I'm shuffling the order of the sequence, it should be having a very different interpretation in its output. So the order should be maintained precisely in the neural network. Also, in text data, it's a very huge type of data. So if I have a parameter being set for each token I might be having billions of hundreds of weights that I need to learn for each token. So in that case, I need to have the kind of parameter sharing. I can move these parameters, these same parameters across the tokens and learn different things from these tokens with the same type of parameters. Okay. Also, in order to use these resources like the GPUs and TPUs, we should enable the parallelism feature. So the learning is pretty much faster than the sequential type of neural networks. So basically, these 5 kind of properties are the top ideal properties that we need in structuring an architecture for the text data. Okay. So let's discuss the fully connected neural network and why it is not efficiently modeling text data. From the first side, you can see here that this structure is not maintaining any parameter sharing. Like, for example, here, the first weight matrix is a 3 by 3 matrix, while the second weight matrix is a 3 by 2 matrix. Okay. So in that case, these parameters are pretty much different from these parameters. So they are not being shared across the layers. Also, the order here is not maintained as the input is being inserted to all the neurons in the first hidden layer, and the same is passed through the next layer. Also, the size of the input should be 3. It shouldn't be anything but 3. If we have 4 inputs, then we should have a different architecture because we need to add another 4 weights to this matrix. So the full architecture will be changed. So basically, it only handles the parallelism because these calculations here doesn't depend on any calculations in the next neuron in this level. So it doesn't need to wait until this calculation or this execution is done. It can be done parallel way. Okay. Let's get to the why the convolutional neural network is not efficient also for handling text data. However, like there exist models using convolutional neural network, but it's not as efficient as the recurrent neural network. But some of these architectures have been raised with using the building models using the convolutional neural network, but it still doesn't have this generalization model. Just a note to make it clear. So basically, the convolutional neural network is built in this architecture. This receptive field or these filters are the weights of the neural network, and as you can see here, they are shared across the image. So if this matrix is the image and we need to transform it into an output, or this activation being activated or receptive field being applied across each filter size of this input and generating this output here. So as you can see here, the defaults, the flows of this structure, it doesn't maintain the order because each of this kernel or this filter is combining all this input into a single number, which doesn't maintain the order of the text. And also it doesn't maintain if another image is being inserted, it will not be correlated with this image. Okay. So, but it can be parallelized. Like this filter this output can be produced in a single shot. Like this filter, because this number doesn't need to wait until this number is being calculated, or any of these numbers are depending on any of the other numbers. So it can be parallelized, and it also have this parameter sharing, but it misses these 3 types. Also, the size of this image shouldn't change. Okay. it cannot handle this variable length size. Also, although these papers like convolution sequence to sequence learning have been raised, I can put through the description of this video so you can see it and look how it performs against the recurrent neural network. Okay, so now let's discuss the recurrent neural network. Basically, it's structured in a simple way. It's just having a meaningful interpretation of the maintaining the order in an elegant way. Like for example here, we are producing an output for each input here, but in the sense of each input is being affecting the following inputs, and the output here is being depending on the previous inputs. So like passing the information in this way to the next tokens is the core strengths of these architectures. Like the main idea is to pass the information to the next tokens and make the neural network aware of the context of the previous information that have been learned during the first part of embedding the sentence. So it have you can say these four features, the four ideal features, but it misses the parallelism. As you can see here, in order to calculate or in order to produce this output, we should wait until this ht-1 is being calculated, which is basically depending on all the previous hidden state and all the previous executions. So this output is depending on the previous output, so it cannot be parallelized by definition. Okay, so let's talk about some of the architectures that has the full, you can see the full 5 ideal parts. Like it can be parallelized, it can have this parameter sharing, and it can also model the variable lengths and also maintain the order in an efficient way. This architecture is called the transformer. We will be discussing it later, and it is basically built for a various type of models like the BERT, the ChatGPT, and the GPT-4. They are all using the structure of this architecture, so we'll be discussing it in next lecture and trying to get into the details of this architecture. But let's dive in the recurrent neural network for now. So, for example, if I have this sentence, since he lived in France for 20 years, he speaks what? So the language model by definition is nothing but learning what to predict the next word giving the previous words. Okay, so this is basically a simple definition of a language model. And in that case, if we need to model, if we need to predict these inputs, then we need to have a learning of all the previous tokens that we have. So for example, here, if you have this type of architecture, and it is called like a many to one, because we need to predict a single token, which is the problem is called the next word prediction, for example. And or it can be a classification, like I can classify this sentence into positive or negative, a sentiment analysis text problem. So in that case, this YT is depending a lot on the previous inputs, and in the matter of that, if the model have this passed the information of this token pretty well through the network, so it can predict easily that he speaks French. So let's get through the forward propagation and how this information flows in a little bit mathematical way. So basically, if we have this again architecture, like it is called the many-to-many architecture, and you can see from here each layer is depending on the previous layer. So the calculation is pretty much depending on the previous state. HT here is the current state, and HT minus 1 is the previous state, and XT is the current input. So to produce the current hidden state, which is called H for hidden, we need the input, the current input, and the information from the previous state. Okay, so in that manner, it is the same function being executed each time step. Also, the Y is only depending on this hidden state. So it's a function also depending on the hidden state, the current hidden state. And if we need to interpret it in this way, like this Y3 is depending on the current input, the X3, and also all the previous inputs, as they are flowing their information in this hidden tunnel through the network. Okay, so let's talk about adding the weights to the neural network. As we have just talking about flowing the information, we need to know how to learn the model. So basically, we will be adding weights to each of this arrow, but these weights are being shared across the layers. So for example here, instead of having just the X and the H, we'll be multiplying them by a weighted matrix, which are the learnable parameters across the neural network. So the neural network is its objective is to modify or to learn or change the basis of these weight matrices in order to produce the most efficient output, or flowing the most important information through this network. That's the main objective of the recurrent neural network, is to flow the most critical or the most recent updated information through the network without any loss. And the same weight matrix will be applied in order to generate the output for each layer. So let's discuss the backpropagation part. What is backpropagation? It is just how the model learns and how these weights are being modified. If you have learned the word gradient, this gradient is nothing but calculating the derivative with respect to the previous input. So for example here, if we have this again architecture of many to one, and we need to predict a single word, and we have this loss function to be an evaluation of the model, the prediction. So when we calculate this loss, we need to modify the weights of these matrices of this neural network. So basically, the gradient will be passing through the neural network in that way. It's called backpropagation through the time because we are getting back through the time until the first input. What are the flaws or what are the issues regarding this approach in order to make it efficient for learning? First, it have one of two issues: whether the gradient is being a huge number, like anything. If this sentence is a very long sentence and we need to pick up information from the first tokens, then we need to make the gradient flow till this point in the first part of the model and change the weights efficiently in order to make this information flow again till the end of the network. The actual problem here is the gradient. If it is small, then it cannot be efficient to modify the weight of the first weight matrices of this architecture. So basically, if this gradient is less than 1, so it will be a fraction, and multiplying multiple fractions with each other, it will be reducing the value of this number with a huge, as each time step we are multiplying it by another fraction. Okay, so each time the gradient will be minimized until it have a negligible change to the weight, which can be reducing our learning by a huge time. So these are the two main problems. Like in the other side, if the gradient is greater than 1, then it will be each time getting bigger and bigger, and this can cause the problem of overshooting, that the model cannot learn well because the model need to learn in a stable type of learning rate. Okay, so having this problem of overshooting can cause the model to learn in an unstable way, but it cannot be guaranteed that it will be learning in the stable to make it in the production with guaranteed predictions. But if we need to manage the gradient exploding, which is having the gradient greater than 1, then we can go with the gradient clipping approach. Like we can put a threshold, and each time any gradient passing over this threshold, we cut it off. And it's working pretty well for the large language models. Like if we when you will be developing with each other this BERT and going through this modeling, you can see there, like, we are clipping the gradient, because if the gradient is greater than 1, we will be having this issue of explosion. And the other part we have talking about, like, is the gradient vanishing, as the gradient is being multiplied by another fraction until it is just being to 0. So no changes, there will be no learning at all in the neural network. So in that case, we will be changing the architecture. It can be other tricks like changing the activation function in order to avoid this drainage of learning, but in most cases we will be changing the architecture of this neural network in order to make the flow of the information more efficient, which is the main objective of the recurrent neural network. So let's start to discuss these LSTM architectures. It is basically one of the huge evolutions of this recurrent neural network. Instead of having a function like the recurrent neural network using the tanh, we will be having this set of functions each time step. Okay, so for example, here we have these 3 inputs instead of 2 inputs. We were previously having the hidden state and the current input as our model input. We will now having a 3 inputs. This new part is called the cell state. Okay, we'll be discussing it later because it's the core strength of the LSTM. This can be called the short-term memory, and also can be called the hidden state. And this will be called the long-term memory or the previous cell state. And the LSTM actually is based on this synonym, like it's called the long short-term memory, because it have these 2 memories going through the cell. And this is the new cell state, and this is the current hidden state, which will be flowing through the next LSTM unit. Okay, so basically we will be passing through 3 gates and moving towards the output in such a way. So each sigmoid will be considered as a gate, and The architecture of this part will be discussed more in details in the next lectures, but just a simple lookup of these gates. Here, each sigmoid here is considered as a gate, because sigmoid is nothing but an activation function that takes any input and map it through 0 to 1. Okay, so if the sigmoid have a result in 0, so it means that the gate closed, and if it is 1 or a fraction greater than 0.5 or something, then the gate is opening. And what does it mean, opening and closing? Like closing, it means like this information will not flow to the next cell, to the next unit. And opening the gate means like flow this information. This information is important in order to interpret the other the prediction of this model. So these gates play a critical role through the network learning, and the network objective is to modify the weights across, because each gate will have a weight. So the network learning will be modifying the weights of each of these gates in order to create best decisions across these gates. So it knows when to flow the information, and it knows when to block the information. Okay, so basically we will be having these 3 gates. They are called the forget gate, the input gate, and the output gate. But let's discuss first the core strengths, as I've said, with this cell state. So this cell state, or the long-term memory, can be considered as the chain which passes through the full neural network and flows the information in a very smooth and elegant way across each unit of the input. So as you can see here, this type, it interacts with the input in such a way of this gate, and also adds information through this gate. So it is multiplied by this gate because this is the forget gate, and we are here removing information from this cell state, which is passing through the full entire chain of the LSTMs. So we are here removing some of the information that are not used or not important, and in this gate we are adding new information from this input, which is called the input gate. And the final gate is getting information from this cell state and producing it to the output. So this cell state will be again passing through different cells, moving the information from each cell to cell in this very elegant way. So let's discuss the forget gate. This is the main part of the forget gate. Here we are multiplying in an element-wise way the cell state. As you can see here, we are multiplying it in an element-wise, point-wise multiplication with this forget gate, and adding it with the input gate. But here, what are we forgetting? Like, for example, if the text is talking about a document, talking about somehow a dog or a girl, and then the context has been changed to talking about a boy. So we are changing here from a female to a male. So in that case, we need to forget about the girl's information and start adding, and then we will be adding in the input gate the information about the boy, because we are changing all the structure of the information, the flow of the information in that manner. We need to update each time the flow of the information with the current input. So you can interpret it in this simple way. Okay, And this is the mathematical interpretation. We are multiplying this weight by the x, the current input, and also here by the previous hidden state, the short-term memory, and applying a sigmoid activation function to see what information we need to filter out and remove it from this cell state. Okay, so let's get to the input state. It is also combining the current and the previous hidden and adding them to the current cell state in order to generate the current cell state, adding it to the previous cell state to generate the new cell state. Okay, so this type of gate is adding information and storing new information inside the chain of the cell state. So it will be having a different weights, as you can see here. It is w.i.i, which is the input to the input, and hi, which is the hidden to the I. Is the dimension of the input, because x here is a vector and h also a vector, but the weights are matrices. And also this activation function is a sigmoid function, like it is this gate. So 0 is unimportant information, 1 is the important information. Okay, and in the other part, it's like we are applying a tanh, and the tanh is a little bit different from the sigmoid, because tanh is producing an output from -1 to 1, which is double the size of the sigmoids, because sigmoid is generating from 0 to 1. So the tanh have this like it is not a pretty much a gate like sigmoid, because it maps the same domain into a larger domain over the sigmoid. So it has this difference, like any change in the tanh can have respectively, like any small change in the x can have a huge change in the y, but in the sigmoid any small change will have a negligible change in the y, but any large change in the sigmoid will be activating the sigmoid. So in order to activate a sigmoid, the changes should be huge, because sigmoid curve is a little bit in a denser way, while the tanh is in a wider way. So the changes will have a different y, different outputs. So this is like a small differences between the sigmoid and the tanh, you can see. And after that, the tanh output activated of the tanh and the activation of the sigmoid are being element-wise multiplicating and passed through this cell state. So we add this information in this manner. Okay, and this is the current cell state, and which will be the current output, but after passing through the final gate, which is the output gate. So the output gate combines also the input and the previous hidden state to the and pass them to the sigmoid, and then element-wise multiplication with the tanh, another tanh activation function across this cell state to generate a hidden state. Okay, so this is pretty much the LSTM. The main flaws of this LSTM, it does have the great flow information across its units, but it doesn't have this fast execution as the recurrent neural network was having, because the recurrent neural network was just having a tanh function to be applied for the input and the previous hidden state, while the LSTM does have a pretty much 3 gates and 2 tanh. So in that manner, it have this delay or the learning of the LSTM is very much slow, and many variants of this architecture have been developed. One of them is the GRU architecture. For example, here we have two inputs only, the X and the previous hidden. We don't have this cell state. And also we had two gates only instead of three gates from the LSTM and one tang. So the GRU is a little bit faster. These are the equations of it. It is a little bit faster over the LSTM, but it's still slow in the learning from the recurrent neural network. Okay. In the next lecture, we will be discussing some about how we can develop these architectures in order to model sequence to sequence or text translation application. So stay tuned to the next lecture and see you there, and goodbye.